I am from University of Poitiers. My origin is from Morocco. I am born in Marrakech. Marrakech is just here, not far. And I am really pleased, and I would really thank Rida, Nicola, and all of the organizers of this nice meeting. Thank you so much, giving me the opportunity to share with you this incredible story. I am not in your field, as you will see in a few minutes, but it's about history of life, and I think all of us were interested to know what is the origin of life and how the first emergence and when and why we have the change and the complexity of life. So this story is a scientific story, but also human story, starting in 2010. So you can be really confident, because I will do my best in order to make everything easy for you to understand. I will not go far in details, and I will give you most of what I can about the interpretation, etc. So, yes, the beginning is, the first thing is to talk about the age of our planet. I don't know if all of you know that the age is around 4.5 billion years ago, so it's very old story. And you know, as you can imagine, at the beginning, before scientific method will be developed, we can have this Earth created on October 23, 4004 before Jesus-Christ at 9 p.m. So I don't know if you believe on this, but if not, you can believe on the scientific datation, and we know that the age of Earth is not like what this very, how to say, religious guys say, but it's 4.5 billion years ago. So it's too long story, and many things happened. Now, Darwin, everyone know who is Darwin. Darwin is working mainly in evolutionism. And thanks to Darwin, we have the transition between theistic science to naturalistic science. So Darwin, at the beginning, he learned first religion, and he changed, and he go in this direction of naturalistic. He changed completely the direction, and he go in the direction of naturalistic science. So it's very important to see how was the trajectory of Darwin, and the hypotheses, different hypotheses suggested by Darwin. So Darwin, he worked a lot, because he's not geologist, but he collaborate with Adams, and they was always in conflict, because one is more biologist and the other one was mainly the geologist. And the main question arises is, why was nothing discovered in the oldest rock? Because all of the life story suggested by Darwin is based around 500 million years, nothing more. So please keep in mind that the age of our planet is 4.5 billion years ago. So Darwin was always asking himself, and debated this with Adam, about why we have nothing older than what we have today. So he lived without any answer. So you know this book, The Origin of Species, very famous theory of Darwin about the life history on Earth, suggesting that the life history is progressing gradually. This is the suggestion of Darwin, because his point of view was focused on 500 million years, not more. Now, if we look at this slide on the left part of side, we can understand that the Darwin had partial view of life history, which is not really a problem, because he need a lot of life, a lot of years to understand what happened. And now the methodology in terms of characterization of datation is developed. So we know that the age is 4.5 billion, and many things happened before 500 million. So if you look at the, I don't know if you see my laser. So we have only small part of life history described by Darwin, but this is not criticism, but just to give you an idea about how it was difficult for him. Now the problem is that Darwin, in this case, he decided to suggest the Precambrian void. Precambrian void for Darwin is all this part which for him is void, nothing. He believed that nothing happened before 500 million. So it was complicated, and it was really, really a big problem for him. But now this empty time is not is solved thanks to several discoveries. Now we will discuss about the start of the beginning. What about the deep biosphere? What happened at the beginning of Earth? So, you know, before to have the first cell, before to have the first molecule, we need to understand what happened on Earth. So around 3.8 billions, there is a lot of heavy bombardment coming from the asteroid meteorite coming on Earth, and something happened probably on the oceanic system, and this is called prebiotic chemistry. Prebiotic chemistry is mean this is the first reaction. We need some kind of atoms, of molecules, before to build anything. If you want to have DNA or something like this, we need to have some kind of chemical reaction. This chemical reaction starts somewhere and sometimes, and it seems that based on this very heavy bombardment, something happened in the Earth system, mainly in ocean. So the hypothesis is probably, and now is confirmed, carbon, phosphorus, nitrogen, all of the elements we need for life is coming from outside of our planet. So our origin, all of us, is extraterrestrial, if I can summarize this like this. So now thanks to the biological colleagues, biologist colleagues in molecular biology, we have this LUCA. LUCA means last universal common ancestor. We need to know what is the first cell on the Earth, starting, the beginning of, in French is le début du commencement, when everything starts. So LUCA is, of course, something virtual, okay, based on modelization, etc., etc. So LUCA seems correlated with this big heavy bombardment of our planet. That's why we have this correlation probably with this event, bringing to our planet all of this element. So now LUCA is virtual as reconstructed by scientific concept, is based on modelization. So the origin of life before LUCA is mainly chemistry. It's called probiotic chemistry. We have the first cell, LUCA, even it's virtual, and since LUCA we have three directions. We have eukaryotic, we have archaea, we have bacteria. All of this word is unicell, monocellular organism. This is the base of the first emergence of life on Earth. So we have these three ancient lineages survives and colonized of the planet till now. We have everything till now. So this is what I would like to discuss, to show you, is the transition between this stage and the next stage in terms of multicellularity when we have this complexity, and why. So LUCA is very, very important, but Darwin is still, how to say, he said that if all cellular organisms are evolutionarily related, they should share a last common ancestor. He's asking himself. For him, it's something happened, because it's for him completely strange to have like something very sophisticated emerged on Earth without anything before. So all of the study on this LUCA is showing that the environment of life of this LUCA is anaerobic, without oxygen, hydrothermal vent, it's hot water. So this LUCA use chemistry like energy. This is what biologists suggest like condition of life of these virtual organisms. Now we need the concrete discovery and life. So the first trace of life is discovered at 3.5 billion years ago, and it's mainly bacteria. And they can show you later how what is the morphology of this bacteria. But before LUCA and bacteria, we have nothing. So what is the crucial shift from unicellular to complex multicellular life is somewhere here at 2.1 billion years. So from 3.5 billion to 2.1 billion, a long time. And many things happened, mainly oxygen story changes radically between this in this interval of time, and they will show you later how this. So this image, for example, of this fossils here is what one of the organisms discovered in Gabon, and they will show you later in details the morphology. So the first step of complex life start here at 2.1 billion years ago, and the next step is around 600 billion years, and it is the Dakara fauna discovered in Australia. But before 2010, before this discovery from Gabon published, our scientific register explained that all of the multicellular complex life start at 600 million, not 2.1 billion years. So it was a big dogma since Darwin theory. So now, if you go to the Cambrian, so the Cambrian is one of the interval of time Darwin used like reference. Of course, if you look at this organism, I will show this organism is coming. Sorry, it's coming from Morocco. Yeah, our scientific term is trilobite. It's like how to say. Yes, they have a lot of appendices. It's very sophisticated organism. And is around 510, 530 million years ago. And they are very, very sophisticated. So the problem for Darwin and for all of us is to find some kind of exceptional geological locality where we can have a nice conservation of life. Otherwise, it will be modelization. And modelization, as you know, it's not reality. We need modelization. But for our field in geology, we need absolutely to find something to confirm what we obtained by models. So we can understand Darwin because he based all of his research on this 500 million, 530 million years ago, because we have very nice biological revolution from static benthic to dynamic pelagic. So he was very impressed by this biota because we have very nice sophisticated life. So he started his theory from this interval of time based on this nice fauna. So this nice fauna is coming from Canada, somewhere in the British Columbia. It's like this kind of mountains with a lot of many nice things. And they discover really very nice and very sophisticated, as you can see here, organism with a lot of details. But of course, the question is, it's absolutely not clear to have something very sophisticated and nothing before. The gap is very big. So I would like to show you, because we are in Morocco, I would like to show you some exceptional biological record discovered 1.5 years ago and published in Science magazine. So it's this very beautiful arthropoda with a lot of appendix, very sophisticated, and they will show you in 3D. You can see here a lot of details. This is conserved by ash deposit because near this place is 510, 550. We have volcanism at this time, and like in Pompeii and Herculaneum in Italy, we have this ash coming on this nice trilobites, and they conserve them in 3D. So it's very easy for us to explain and to describe. And I want to show you in 3D animation. It is not ChatGPT, believe me. This is a 3D scan with X-ray tomography. So we scan this organism coming from Morocco, and we have a lot of details. Everything is really well conserved, everything. So it's for us really nice discovery because it permits us to understand and to suggest something with very clear and very concrete suggestion. And we obtained, thanks to the team, the cover of Science, it's very nice for geological heritage of Morocco. Now I would like to summarize very quickly the short history of our planet. So the beginning is very volcanic, very hot. a lot of activity of volcanic activity. And around 3.8, we have the beginning of hydrosphere, ocean is coming. And we have a big event coming around 2.4, 2.5 is a very big glaciation. And this big glaciation was really very important because after this glaciation, the oxygenation on the atmosphere of Earth changed totally. Before we have anoxic, without oxygen. Our planet was without oxygen. But after this glaciation, the oxygen increased, and this increasing of oxygen is correlated with 2.1 billion years. This is the age of the geological formation we study in Gabon. The same glaciation occurred somewhere around 700 million years just before this beautiful fauna in Australia. So before Gabonese biota and before Australian biota, we have two big events with nice big glaciation. So this glaciation initiate a lot of alteration from continent, a lot of nutriment come into the ocean, and we have increasing of cyanobacteria. Cyanobacteria is like vegetation today. They create photosynthesis and they produce oxygen in the atmosphere. Although of the oxygen we have today, the origin is originally from cyanobacteria. So you can understand that there is nice correlation, co-evolution between environment and life. So now we can go for this complex early biosphere. And I would like to show you the geological context. Believe me that I will not go far in details. I want just to show you Gabon. The Gabon country is somewhere in western part of Africa, and all of the colors you have on this map is just showing for you that we have different age, different geological context. So that doesn't work. The circle is the place where we are working in the southeast part of Gabon. Is very big basin, the age dated 2.1 billion years. Now, this place is absolutely exceptional because believe me that it was really, really difficult because working on 2.1 billion years rock old, so showing that we have a nice consideration is not easy because the oldest rock normally is supposed to be transformed. In this case, it's absolutely incredible. So 2.2 billions, the rock, this interval of time is called the middle age of Earth because if you calculate between 2.4 billions and today, we are somewhere in the middle. Voilà. So we have excellent conservation of sedimentary rocks. This is really for us like very good argument to study and to show what we have. We have exceptional accumulation for manganese. Is like in Morocco, we have phosphate here. They have manganese in Gabon. And they have something exceptional. We don't have time to explain this. They have the natural nuclear reactors. So we don't have time to discuss about this, but this is absolutely exceptional event occurring in the same time on where we have this nice biological record. So now when we start studying in Gabon, it was like this. Our knowledge was what we have here is what is the multicellularity. Is individuality, coordinated growth, size, increase in size, diversity, occurrence around 600. It's not 2.1 billions. So it was for us, when we start, it was what we have in the literature, nothing more. Now I want to show you what is the state of art about the early biosphere. So if I summarize what I explained for you at the beginning, 3.8, we have LUCA, last universal common ancestor, this virtual organism. The first races bacteria is around 3.5. And before our work in Gabon, it was empty, nothing, absolutely nothing. Something around 1.5. And we have this Ediacaran Australian things around the material fauna at around 600 millions. So I am interested by all of this very old part because since 500 to now, it's very well known, and Darwin did a lot. Now I want to show you the morphology of this bacteria. As you can see here, is very small. It's not absolutely visible. It's microscopic material. It's filamentous material, And, bacteria is still today. The first races is around 3.5 billions. And we have also bacteria at 1.9. So it's look like this. It's very, very small. Team from Belgium discovered something in South Africa. Is this nice cell. It's very microscopic things. It's around 20 micron in size. And they interpret this like algae or big bacteria. But it's 3.2 billions. Please believe me that it was absolutely nice discovery because, no, Darwin is always thinking about nothing before. Now the different discoveries show that there is many things happened before. Now we have this nice algae. Gripania spiralis is around 1.6, 1.7 billions. We have this very nice tube from India, 1.6. The interpretation sometimes is difficult for us because we don't know if it is bacteria, if it is algae, if it is fungi, but it's life. It's 1 millimeter, it's not too big, but it's life. And we have also this nice discovery, 1 billion. It's a Chinese colleague. They published this in Nature, it's Nature paper, and they show this very nice algae. The age is around, yes, it's 1 billion. So, we are covering all of this empty space. And of course, we have this very famous Ediacaran from Australia. Now, what is the contribution of Gabon? Gabon is, how to say it, it's tropical country. And when we start working, it's a lot of vegetation. And here we have a quarry. And inside this quarry, you can see that there is something like 15 meters thick and about 5 meters thick. And we go there just for geology, not for looking anything. It was just because there is nothing at 2.1 billion. It's 600. And we start working because the problem of equatorial country is it's very humid and a lot of alteration. So, we are trying to make this quarry clean, as you can see here. And, just to give you an idea about the humidity, we are in Gabon, so it's sometimes very hot, even all the time. So here, the objective is to obtain something like this. As you can see here, we have like sedimentary beds, like a book. We have just to open and to see if there is something inside. So the big question, when you suggest something, they will ask you about biogenicity. What do you mean biogenicity? Please prove to us that it is biological record, because normally at 2.1 billion years, there is nothing. So we use first the morphostructural characterization based on this type of morphology. So this is our first discovery. When you observe this kind of material, of course, you have two possibilities. One is you are curious, you sample them, or you say, okay, at 2.1 billion years, there is nothing, and you leave. So what we decide to do at this time is to bring them and to analyze them. So to analyze them, it's not very easy. That's why we need absolutely some kind of sophisticated machine, and we use this scan, and this scan permits us to have the morphology like this. Here we have the organism like we bring it from the field, and here we have what we obtain by scan. And the scan is very helpful for us because it permits us to see in 3D what happens, and we can cut in different way, but it's virtual cut. We conserve the specimen, but we can cut it in different way. Why? Because we need to see in details what happens. And this is very new and very sophisticated machine. So look at this. We have more details by using this scan. And even we can go in 3D. I hope it will work. Jeunes hommes qui sont là-haut. Ah, ça n'a pas marché. Pourquoi? Dommage. Ça a marché tout à l'heure, ça n'a pas marché maintenant. Régie. So voilà. Bon, c'est pas grave. Si, it's coming. Here we have 3D animation based on scan. You have the specimen on the left is 5 centimeters in terms of length, and we have the print at the right side. And now, based on by using software, we can bring them segmentation, bring them from the rocks, from the bedding around, and we go in details in 3D. So we can cut it in different way. Here we have transparency. Why we use all of this is not just to make something like joli. No, we would like to see in details all of this. For example, all of this radial fabric we cut, for example, in this direction. We would like to see if this radial fabric around is fracturation or it is something inside the specimen. So we cut in different way. And we see what happened. For example, we focus on this wrinkled part and the center part of the specimen. All of this, for example, here we are cutting in transversal way, and we are looking for this radial fabric, and we understand that this radial fabric is located on the edge. So this radial fabric seems that there is some functionality. That's why we interpreted them like benthic. Benthic means that it's living on the sediment. It's not a planktonic, it's benthic. So this is one of the nice discovery. The other one is to see if there is any variability in terms of size and shape. And I can show you that we have a lot of morphology. We have something around 16 morphotype, different morphotype. For example, this one is 18 centimeter length. It's very, very, very long specimen. We have this one obtained, this image is obtained by X-ray tomography, and you can see that we have very nice, for example, here we have very nice wrinkled part, we have this elongated part, and it's something around 8 centimeter, and we have planktonic life, for example, this one, I show you at the beginning, and we are in 2.5 centimeter in terms of diameter, and if you look in 3D dimension, it looks like, how to say, like Medusa. It's very big, and we can see that we have a lot of details. All of this criteria is called biogenicity, because all of the reviewers will ask you, please prove that it is live. And we have this artistic reconstitution to show how this organism survived. We published this work 2 years ago. And we have also, like what they found in South Africa, this kind of small algae or small bacteria. We have no idea what is it, but it's something living at the top of the seawater. Now, more cell complexity and trace of mobility, something was very, very intriguing for us. We have this some kind of elongated specimen. We have print counterprint is around 20, more than 10 centimeters in length. And here we have 3D characterization. We can see if there is mobility or not. To observe this, we need absolutely to cut in different way. So this is what we obtained by X-ray tomography. We put our samples inside machine, like when we are in the medicine, we are inside the scan, and we'd like to see what happened in the earth, in the heart, what happened here. So here we have exactly what we have inside the rocks. And we discovered that we have this kind of tube going inside the rocks in different direction. Now the interpretation is, for example, here we are cutting in this way, and we are looking that we have, for example, fair. Voilà, sorry. All of this yellow level is cyanobacteria. All of this. Oh, c'est pas possible ça. Pas l'habitude de ce truc-là. Hop, voilà, sorry. Je vais essayer d'être. Faire attention. Ça c'est. Here is where the cyanobacteria. Okay. And we are taking out all of the host sediment because we would like to see what happened inside. And you can see that there is cyanobacteria, and we have our tube, and our tube is going inside, and we have this sinuous trajectory. And if you look at the top here, you can see that sometimes we have some vertical tube. So if you are a geologist, the first interpretation you will have is motility. But motility at 2.1 billion years, it's just incredible. So we did a lot, not only in terms of morphology, but we analyze geochemistry, we analyze petrography. I don't want to give you all of these details because it's more specific to geology. But it's absolutely incredible. And we decide at the end to see if this trajectory is it's going like constant trajectory, or it is some kind of biggest and thinnest, etc. So we decide to put the camera inside the tube, and the diameter of the tube is just 5 millimeter, 6 millimeter, and we go inside. We go inside the tube trajectory, and we see what happened around. So this was interpreted like motility, trace of motility, and it was published in PNAS. So 3D characterization is helpful, but it's not enough. That's why we use a lot of other techniques in order to characterize all of this. Now, who is responsible for this movement? So in this paper, we suggest, for example, that could be the aggregation of amoebae, and amoebae in terms of when the environment is, when they are in stress, they move because they need absolutely to have, they join their force, complexity, and they try to find more oxygen together, more nutrient together, because the system is becoming more and more difficult. Now, if you summarize all of this, we can just have this list. We have elongate, lobate, tubular, circular, surrounded morphology. We have rod and string morphology, organisms like the circular one, and we have this small organic world architecture. So this development of complex life, multicellular life, it was not coming by chance, but it was like, voilà. I understand that I am at the end. This is this 2 times where we have this increase of oxygen, and we suggest our hypothesis is there is a link between oxygen story and the development of biological record. So now, if we come back to this organization, we have Luca, we have the first traces, we have the complexity with the Gabonese story, we have this algae, and we have the second complexity. So what it was called the empty age without anything by Darwin is now somehow coming progressively by different, completed by different discovery. So it is the oldest biodiversity of complex multicellular life in well-oxygenated environment. So oxygen played a big role in this story, but it's not enough. It's not enough because when you have this kind of morphology, when we have this kind of life, it's soft body. It's soft body. There is absolutely no test. There is no calcareous thing around. It's really soft body like Medusa. So the conservation is very hard and very difficult. You need very specific condition if you want to have these nice and beautiful organisms. So the team is an international team. It's African, it's European, it's from everywhere. And I'm really, really happy to have this team with me because we are involved in the formation of the PhD student, and we share all what we did with these people. And when I go to Gabon every year, I share with the authority all what I am doing, and I involve them on all of our activity at the University of Poitiers. J'ai encore un peu de temps? So it's not finished because I want to give small things asked by my friend Rida about Anthropocene. I want just to introduce Anthropocene, but I will not go in details. So I want just to show you what happened billion years after this complexity. So the history of Anthropocene is what Rida started to show us yesterday. The Anthropocene is, the activity is human activity. So as I showed you before, the 4.5 billion years ago till today, it's a long time, and we know that the life is not, Darwin suggests that it's gradual evolution. It's not gradual evolution. It's something increasing, but when the condition of environment is not okay, the life stopped and we have extinction, we have biological crisis, and when the condition become favorable, we have increasing of life, etc., etc. It's like, in French, marche d'escalier. So this is so now everyone here, we are discussing about the impact of human on our planet. So humans shape their environment, of course, by cultivating, building. We transform our environment. And the Anthropocene tell the story of this collective imprint, which is scientific, ethical, and symbolic. So the humanity leaves its mark in stone, and we know that. So we leave memory, language, we reshape our environment, we reshape our planet. So the Anthropocene invite us to reflect on our power, on our responsibility toward the living world. So the major stage of Anthropocene is how to say, Anthropocene it was a big debate about this term, because I will show you later when this term was suggested by scientists. Some colleagues believe on this, some other no. But now when we look all of the transformation, all of the changes on the earth, we have nice correlation between industrial revolution and the increase in all of this gas and all of this greenhouse story, all what we live in today is absolutely correlated with the industrial revolution. So Earth has memory. Of course, Earth has memory because all of our activity is impact environment as is recorded inside the rocks. So that's why our role like geologists is to try to reconstruct what happened before. So we try to understand by analyzing mineralogy, chemistry, biology, if there is any change, if there is any impact on environment. And of course, we observe that there is many transformation. So just to finish with this slide, Buffon, I don't know, you know him, he published some book, Les Époques de la Nature. So it's 18th century. He said that the interface of the Earth today bears the imprint of human power. So he gave the Anthropocene definition before everyone. But in 2000, Eugène, biologist, chemist, they suggest this term. This new geological phase is triggered by the Industrial Revolution. It's characterized by humanity's capacity to transform the entire Earth system. So today we don't have time to go far in this, but believe me that it's a very nice story. And now we have a lot of information showing that clearly we have nice correlation between industrial revolution and the changing and the environment of our planet. Thank you so much. Thank you so much.